In 1992, astronomers announced something that should not have existed. The first confirmed planets ever discovered outside our solar system were orbiting a corpse, not a fading star, not a dim red dwarf, a dead star. It is a pulsar, the collapsed remnant of a star that exploded and died, now spinning 161 times every second while firing beams of radiation across the galaxy. And astronomers did not find its planets by looking for them. They found them by listening to a clock. The pulsar's radio pulses arrived with such extraordinary regularity that scientists could predict exactly when the next one should appear. Then something began disturbing that rhythm. Three invisible worlds were pulling on the corpse. Their names sound less like planets than warnings: Draugr, Poltergeist, and Phobetor. Draugr is the smallest confirmed exoplanet ever discovered, orbiting a stellar remnant only about 20 kilometers, which is about 12 miles across. That entire object contains more mass than our Sun. A single teaspoon of its material would weigh roughly 10 million tons on Earth, and every 6.2 milliseconds, the star completes another rotation. The three planets should have been destroyed when their star exploded. The explosion released an unimaginable amount of energy in seconds, enough to match everything our sun will radiate across its entire 10 billion year lifetime. Anything nearby should have been vaporized, but these worlds survived. Or perhaps they didn't. One possibility is that they somehow endured the explosion. Another is far stranger. They were destroyed and then rebuilt themselves from the debris left behind. And there is a third possibility. These planets may have formed from material the dead star stole from another star before its final collapse. Three worlds orbiting something that should have destroyed everything around it. A star that died, but somehow left planets behind. A planetary system built around a corpse. And the deeper we look, the less certain we become about which story actually happened. A like? A subscribe? Whatever feels right. It all helps this channel reach more people who love falling asleep to the sound of the universe. Let's start with the moment the star died. A star can spend millions of years preparing for a single second, long before it became the pulsar designated PSR B1257+12. Its interior followed a sequence of increasingly difficult nuclear reactions, each demanding greater heat and pressure. Hydrogen fused into helium. Then helium became carbon, and carbon fed reactions producing heavier elements. Deeper inside, separate layers burned simultaneously, creating neon, oxygen, silicon, and eventually iron. The star had become a set of nested furnaces, each operating at a different depth. Iron marked the boundary. Fusing iron does not provide the energy needed to support the star against gravity. Once enough iron accumulated, the core could no longer maintain its balance, and the collapse became unavoidable. For the star, this was a change measured in less than 1 second. A region comparable in volume to Earth collapsed inward until its matter occupied a sphere only a few miles across. Electrons were forced into protons, producing neutrons and releasing an enormous burst of energy. Then the outer layers arrived. They crashed toward the collapsing center and encountered matter that had become extraordinarily difficult to compress. The rebound launched a shock wave through the remaining star, tearing through layers that had taken millions of years to build. The resulting core collapse supernova sent material outward at thousands of miles per second. Radiation surged ahead of the debris, carrying enough energy to transform nearby planetary environments. Worlds close enough could lose their atmospheres, suffer catastrophic surface heating, or be destroyed outright. You can imagine the original system as a place suddenly divided by distance. Far from the explosion, objects might remain gravitationally bound. Closer worlds faced a much harsher outcome. Their survival depended on where they were when the star released its final energy. At the center, something remarkable remained. The former iron core had become a neutron star, preserving a large fraction of the star's mass inside a body roughly 12 miles across. Its matter was no longer arranged as ordinary atoms, and its density belonged to a regime we cannot reproduce on Earth. At the surface, the pressure would be immense, while beneath it, neutrons could exist in forms unlike anything found in familiar matter. For us, this is where ordinary stellar physics gives way to nuclear physics on a planetary scale. Gravity now shaped everything around it. The remnant's rotation also accelerated as its enormous original size collapsed inward, concentrating angular momentum into a vastly smaller object. The star's life had ended, yet its core had acquired a new physical identity. It could no longer shine through sustained nuclear fusion, but it retained mass, magnetic energy, and an extraordinary rotational speed. That transformation left behind more than a stellar corpse. It created the compact object around which an entirely unexpected planetary system would eventually be measured. For the original planets, the supernova was an event measured in moments, but its consequences lasted billions of years. As the stellar layers rushed outward, each world encountered a different combination of radiation, debris, and changing gravity. The closest planets would have faced temperatures capable of destroying rock itself. At distances around 1 astronomical unit or less, the incoming energy could drive solid material directly into vapor. Any atmosphere would have disappeared first, followed by oceans, crust, and eventually the planet's surface. Farther away, another danger emerged. The explosion removed a substantial amount of the original star's mass almost immediately, weakening the gravitational pull that had governed the planets for millions of years. A distant world could remain physically intact while losing the orbit that once held it. With less mass anchoring the system, some planets could have been thrown into interstellar space. Survival, however, was never completely impossible. A planet's outcome depended on its distance, orbital position, and the direction of the explosion. Core collapse supernovae are asymmetric events, with energy and matter distributed unevenly rather than expanding as a perfectly uniform sphere. A world positioned within a less energetic region could therefore receive a substantially smaller dose. There is another possibility, and it changes the meaning of survival entirely. Some of the material blasted outward would have remained gravitationally bound to the newborn neutron star. Instead of escaping forever, that debris could have slowed, curved inward, and settled into orbit. Astronomers call this structure a fallback disk. It is a rotating collection of gas and stellar debris captured by the remnant after the explosion. Given enough material and enough time, gravity can gather that disk into larger bodies through accretion, the gradual process by which orbiting particles collide, merge, and build increasingly massive objects. That process usually belongs to young stars and their surrounding disks. Here, it could have operated after stellar death. Imagine the distinction from the perspective of a planet. One world might have endured the original explosion, another might have been destroyed completely, with its material later becoming part of something new. The final planet could therefore carry a history that begins before the supernova and continues after it. Over thousands or millions of years, debris could have cooled and collected into solid bodies. Heavy elements forged inside the original star would have become ingredients for new planetary material, while carbon, iron, and other elements were concentrated within the disk. Such worlds would carry two separate chapters of stellar history. Their ingredients were processed inside a massive star, scattered by its death, and then gathered again by gravity. The planets around this pulsar may therefore represent more than survivors of catastrophe. They may be evidence that planetary systems can emerge from destruction itself, with worlds assembled from material that had already belonged to a star. There is a point where ordinary ideas about matter begin to fail. Inside the pulsar designated PSR B1257+12, pressure has compressed stellar material into a state unlike anything found naturally on Earth. Its entire body spans only about 12 miles, yet it contains between 1 and 4/10 and twice the mass of our Sunday. You could cross its diameter in minutes by car. The comparison ends there, because the surface gravity would be approximately 200 billion times stronger than Earth's. A person weighing 150 pounds would never experience that environment normally. The gravitational force would overwhelm the body almost instantly, compressing matter to extraordinary densities. Even the surface itself behaves according to physics far removed from familiar rock and metal. The crust consists of nuclear matter arranged into an intensely packed crystalline structure. Atomic nuclei are pressed together so closely that the resulting material may be stronger than anything humans can manufacture. Beneath that crust, pressure increases until individual neutrons dominate the matter. Here, something especially strange may occur. The neutrons can behave as a superfluid, a quantum state capable of flowing with essentially no internal friction. In such matter, particles do not behave like the atoms and molecules surrounding us. Their collective behavior follows the rules of quantum mechanics on a scale large enough to shape an entire star. Deeper still, the interior becomes uncertain. The pressure may become sufficient to break neutrons apart into their fundamental constituents, known as quarks. Physicists call this hypothetical state quark matter. We have never observed it directly inside a neutron star, so the deepest structure of these objects remains an active question. There is another feature that makes this particular remnant unusual. It rotates hundreds of times faster than an ordinary young neutron star, placing it among the class known as millisecond pulsars. Its rapid rotation is thought to result from a long period of accretion, meaning matter from a companion star gradually fell onto the neutron star and transferred angular momentum. Over immense stretches of time, that process can transform a slowly rotating remnant into an object spinning hundreds of times each second. The dead star effectively receives rotational energy from material that once belonged to another star. That possibility gives the system an unusual history. The companion that helped accelerate the pulsar may also have supplied material that later settled around it. If so, the same stellar relationship that changed the neutron star's rotation may have helped provide the raw ingredients for the worlds now circling it. We therefore have a strange sequence written into one system. A massive star becomes a neutron star, a companion feeds it, and material from that stellar interaction remains available for planetary construction. The planets are part of that history, whether they survived the original catastrophe or formed afterward. A pulsar gives astronomers something unusual to measure: time itself. Each rotation sends electromagnetic radiation outward from its magnetic poles, and because those poles are tilted relative to the rotation axis, the beams sweep across space like rotating searchlights. When one beam crosses Earth, radio telescopes record a pulse. For the pulsar designated PSR B1257+12, those pulses arrive 161 times each second, with extraordinary regularity. That rhythm turns a distant stellar remnant into a natural clock. For astronomers, the important detail is not simply that the pulses repeat, it is that they repeat predictably. A pulsar drifting through space without companions should produce a timing pattern that can be modeled with remarkable precision. Even tiny departures from that pattern can carry information about something orbiting the pulsar. Picture the pulsar moving slightly toward you. Its pulses arrive a little sooner. As it moves away, they arrive a little later. This is the Doppler effect, the same basic change in observed frequency that affects sound from a passing vehicle, applied here to the arrival times of radio pulses. An orbiting planet creates that movement through gravity. The planet does not need to be visible. Its gravitational pull makes the pulsar wobble around the system's shared center of mass, producing a repeating pattern in the pulse arrival times. Aleksander Wolszczan found exactly this kind of pattern in observations of the pulsar. The deviations were measured in microseconds, each representing only 1/1,000,000th of a second. Yet repeated over months, those tiny differences formed a recognizable rhythm that could be tested against orbital models. This is where the method becomes extraordinary. We are trying to infer the presence of a planet from timing changes so small that they disappear almost completely within ordinary human experience. A signal that lasts less than the blink of an eye can still reveal the gravitational motion of an entire world. The Arecibo Observatory provided the sensitivity needed to make those measurements. Its enormous radio dish gathered enough signal from thousands of light years away for Wolszczan to compare pulse arrival times with exceptional precision. The technique also reveals something important about planetary detection. We often imagine finding another world by seeing it cross its star or by measuring the star's motion through changes in its light. Pulsar timing works differently. The planet can remain completely unseen while its gravity writes a signature into the pulsar's clock. For you, the remarkable part is how little information was required. No photograph of a planet, no visible atmosphere, no reflected sunlight. Just pulses arriving at slightly different moments, again and again. From those fractions of a second, an orbital system emerged in the data. The planets had no need to shine brightly enough for us to see them. Their presence was carried by gravity, encoded in time. In January 1990, Aleksander Wolszczan was studying pulsars at the Arecibo Observatory in Puerto Rico. The enormous radio telescope was being used to measure stellar timing, and Wolszczan had a straightforward objective: understand how these rapidly rotating remnants behaved over time. Then the data began to resist explanation. Individual pulse arrivals differed from the expected schedule by tiny amounts, and those differences were too organized to dismiss as random variation. Across repeated observations, the timing shifts followed patterns that suggested something was moving around the pulsar. Wolszczan had found an unusual signal, but an unusual signal was not automatically a planet. Pulsars themselves can produce timing irregularities called glitches, sudden changes associated with disturbances inside the neutron star. A mistake in that distinction could turn an instrumental, artifact, or stellar event into a false discovery. So the evidence needed another set of eyes. Wolszczan contacted Dale Frail, an astronomer working with the Very Large Array in New Mexico, and independent observations began. The second instrument reproduced the timing behavior, strengthening the case that the pattern came from orbital motion rather than the telescope. By January 9, 1992, the evidence was strong enough for publication. Wolszczan and Frail reported two planetary companions orbiting the pulsar designated PSR B1257+12 in the journal Nature. The discovery established the first confirmed planets beyond our solar system. There was still a problem. The astronomical community had good reason to remain cautious because extraordinary claims required evidence that could survive independent testing. Wolszczan approached the uncertainty mathematically. Instead of simply arguing that planets were present, He calculated how their gravitational influence should alter future pulse arrival times. That prediction created something far more powerful than a convincing pattern. It created a test. If the proposed planets were real, the pulsar's timing should change in specific ways at specific moments. By 1994, those predicted variations appeared in subsequent observations within the expected measurement limits. The results strengthened the planetary interpretation and helped establish the third companion, the object later named Draugr. The system became the first confirmed multi-planet system discovered beyond our own, and its importance extended beyond the number of worlds involved. Wolszczan had demonstrated that planetary masses could be detected through timing alone, even when the planets themselves could not be directly seen. 3 years later, another discovery would find a planet around a star much more familiar to us, designated 51 Pegasi b. That discovery became the first confirmed planet orbiting a sun-like star, and later received the Nobel Prize in Physics. Wolszczan's earlier discovery did not receive the same recognition from the Nobel Committee. The scientific reasons for that distinction have remained debated, while the observational achievement itself remains firmly established in astronomical history. Draugr occupies the innermost orbit of the three known planets, following a path only a fraction of the distance between Mercury and the Sunday. Its estimated mass is about 2% of Earth's mass, making it roughly twice the mass of our Moon. That makes Draugr remarkably small. Among confirmed exoplanets with measured masses, it remains the lowest mass world known. We can place that number beside familiar objects and see how unusual it is. A planet can be tiny by cosmic standards and still exert enough gravity to reveal itself from thousands of light years away. Its orbit carries it around the pulsar designated PSR B1257+12 at roughly 19/100ths of an astronomical unit. One complete circuit takes about 25 days. Draugr moves quickly through its orbit, completing more than 14 circuits during one Earth year. The name comes from Old Norse mythology. A Draugr was an undead being with physical form, strength, and a disturbing refusal to remain buried. The designation fits the planet's circumstances with unusual precision because its existence challenges the expectation that a supernova should erase nearby worlds. We do not know what Draugr's surface actually looks like. Its small size makes direct characterization extraordinarily difficult, and no image has revealed its terrain. Any description must therefore remain grounded in physics rather than imagination. At its orbital distance, the planet receives an intense stream of high-energy radiation from the pulsar. X-rays and gamma radiation can break apart molecules, alter minerals, and damage complex chemistry. If Draugr possesses an atmosphere, maintaining it would be difficult under such sustained bombardment. The pulsar also produces energetic particles that travel outward through the surrounding system. Over immense periods, those particles could strip exposed gases from a small world, especially one lacking a substantial magnetic field. Yet the planet's interior presents another possibility. Beneath whatever surface remains, layers of rock could provide shielding from radiation. Depth changes the environment dramatically, because surrounding material absorbs incoming particles and high-energy photons before they can penetrate farther. For a world this small, internal heat would also be important. Residual energy from formation and radioactive elements could provide limited warmth beneath the surface, even while the exterior remains exposed to the pulsar's radiation. Draugr, therefore, sits at an unusual boundary. It is small enough to challenge our intuition about what qualifies as a planet, yet massive enough for gravity to place it in a stable orbit and make its presence measurable. Its existence also gives the word planet a broader meaning. A planet does not require oceans, clouds, vegetation, or a welcoming atmosphere. It only needs to be a world shaped by gravity, moving through space under the influence of another body. Draugr fulfills that definition from a place where almost every familiar condition has disappeared. It remains a planetary body, following its orbit again and again, while the pulsar continues to illuminate its path with radiation rather than sunlight. Poltergeist occupies the middle orbit, positioned between the smallest inner world and the more distant Phobetor. Its gravitational influence was the clearest planetary signal in Aleksander Wolszczan's timing measurements, making it the body that helped reveal the architecture of the entire system. With about 4 3/10 times Earth's mass, Poltergeist belongs to a class known as a super-Earth. These worlds are larger than Earth, but smaller than Neptune, and they appear frequently throughout the galaxy. Our solar system happens to contain no planet occupying this particular size range. Poltergeist circles the pulsar designated PSR B1257+12 at roughly 0.36 astronomical units. One complete orbit takes about 66 and 1/2 Earth days. From that distance, its gravitational pull produces a measurable movement in the pulsar itself. That movement is extraordinarily small, yet the pulsar's timing is precise enough for astronomers to detect it repeatedly. Every orbital cycle leaves another trace, allowing the planet's mass and path to emerge from patterns in the arrival times. The name Poltergeist comes from German folklore, describing a supernatural presence associated with physical disturbances. Objects move, sounds appear. Something unseen makes its existence known through effects on the surrounding world. That description fits the discovery almost perfectly. We never needed to see Poltergeist directly. Its presence became apparent through what its gravity did to another object. The planet itself remains deeply mysterious. Its mass suggests enough gravity to produce a substantial interior, potentially separating dense material into different layers. A rocky composition could create a structure with a core, mantle, and crust. Although other possibilities remain open, we cannot yet determine what those layers contain. The planet's atmosphere, surface, and detailed composition have never been directly characterized through spectroscopy. Without that information, we cannot tell whether Poltergeist is dominated by rock, metal, ice, or materials created from heavily processed stellar debris. Its relationship with Phobetor adds another layer to the system. Their orbital periods appear close to a 3-2 resonance, meaning Poltergeist completes roughly 3 circuits for every 2 made by the outer planet. Orbital resonances can create repeating gravitational relationships between worlds. Each planet repeatedly encounters the other at particular positions along its orbit, allowing their mutual gravitational influences to remain organized over immense periods. For Poltergeist, that relationship may help explain the system's long-term stability. The planets are not simply moving independently around the pulsar. Their orbits interact, exchanging tiny gravitational influences while maintaining a persistent arrangement. Think of the system as a set of moving clocks. Each world follows its own rhythm, yet their cycles remain connected through gravity. Poltergeist occupies the center of that arrangement, massive enough to leave a strong imprint on the pulsar's timing and closely coupled to the planet farther out. We know Poltergeist exists because its gravity changes the motion of something we can measure. Everything else about its physical world remains hidden, waiting inside the mathematics of an orbit we have been able to reconstruct from afar. Phobetor occupies the outermost confirmed orbit in the system, carrying about 3 9/10 times Earth's mass. Its path lies roughly 0.46 astronomical units from the pulsar, and one complete revolution takes about 98 days. The distance gives Phobetor a slightly different relationship with its parent star. It receives less radiation than the inner planets, yet the environment remains extraordinarily energetic by terrestrial standards. The pulsar continues to dominate the space around it, while Phobetor follows an orbit measured with remarkable precision. Its name comes from ancient Greek mythology. Phobetor belonged to the Oneiroi, the spirits associated with dreams, and was linked with animal forms appearing in unsettling dreams. His presence represented a kind of instinctive dread, something difficult to describe and impossible to give a human face. That makes the name fitting in another way. Phobetor is the least physically characterized of the three confirmed worlds. We know its mass and orbital behavior, but almost everything beneath those measurements remains uncertain. No telescope has resolved its surface. We do not know whether the planet is rocky, metallic, icy, or dominated by some unusual mixture produced from stellar debris. Its atmosphere, if one exists at all, has never been directly identified. Even its radius remains difficult to determine with confidence, leaving its density uncertain. That uncertainty matters because mass alone cannot tell us what kind of world Phobetor became. Two planets can contain similar amounts of matter while having radically different interiors. One might possess a dense metallic core, while another could contain layers rich in lighter materials. There is also a possible fourth presence farther out. Some analyses of the pulsar's timing data have produced a signal consistent with another planetary companion at roughly 2.8 astronomical units. The evidence has not remained consistent enough for that object to be accepted as confirmed. For now, it belongs to the category of possible worlds. If the signal represents a real planet, its distant orbit would place it far beyond Phobetor, where the pulsar's radiation is weaker. Yet distance alone would not make it hospitable. The surrounding environment would still be governed by the energetic remnant at the center. The uncertainty surrounding that candidate reveals something useful about pulsar astronomy. Tiny timing variations can preserve evidence of objects thousands of light years away. But separating genuine planets from subtle stellar behavior requires years of observation and careful analysis. Phobetor itself presents no such ambiguity. Its gravitational influence has been measured repeatedly, its orbit is established, and its place within the system is secure. Beyond it, however, the planetary census becomes less certain. From the pulsar to Phobetor, the confirmed system fits inside a region smaller than Mercury's orbit around our Sunday. Three worlds occupy that compact space, each following its own path around the same stellar remnant, while the possibility of another world remains suspended farther out in the data. Imagine placing your feet on Poltergeist, beneath a sky unlike anything Earth has ever offered. There would be no familiar sunrise, no blue horizon, and no glowing disk hanging above the landscape. The pulsar designated PSR B1257+12 produces very little visible light, so human eyes would have almost nothing to see. Your surroundings would therefore be shaped mostly by the absence of ordinary illumination. Without a substantial atmosphere to scatter incoming light, the sky would offer no broad twilight or colored horizon. Stars beyond the system could remain visible, but the landscape itself would receive little reflected light from its parent object. The pulsar would be difficult to see directly. Its physical size would be tiny at that distance, and most of its radiation arrives outside the wavelengths human vision can detect. Yet instruments could track its position through pulses of high-energy radiation arriving 161 times each second. You would never see those pulses with your eyes. Their effects belong to another part of physics. X-rays and gamma radiation can break apart complex molecules, damaging biological tissue and altering exposed materials. A protective suit would need substantial shielding before a human could remain on the surface for any meaningful period. Temperature would tell another part of the story. With almost no useful warmth arriving from the pulsar, the surface would depend largely on energy stored within the planet itself. Residual heat from formation and radioactive decay could continue supplying energy beneath the crust, although the exposed terrain would have no Earth-like climate. Poltergeist would also lack the processes that continually reshape our own planet. Without liquid water flowing across the surface, and without familiar atmospheric weather, erosion would become extremely limited. Craters could remain for immense spans of time, preserving impacts that occurred long before humans existed. A geologist standing there in suitable protection would encounter a record written directly into the ground. There would be no forests hiding ancient terrain, no rivers cutting valleys, and no oceans burying older landscapes. Each exposed impact would add another layer to the planet's physical history. Gravity would alter the experience further. Poltergeist contains several times Earth's mass, so its surface gravity could be substantially stronger than ours, depending on its still uncertain radius. Every movement would require more effort, and even a simple step would carry a different physical rhythm. Above that unfamiliar terrain, the pulsar would continue its rotation. You would stand on a world orbiting an object that sends radiation through the system while offering almost none of the warmth that makes Earth recognizable. The landscape would remain exposed to space, preserved by the absence of weather, while beneath your feet, the planet's interior could continue releasing the faint energy left from its formation. Radiation reaches Poltergeist from every direction, carrying energy that would overwhelm any familiar biological environment. The pulsar designated PSR B1257+12 produces intense X-ray emission, far beyond what we experience from an ordinary sun-like star. At Poltergeist's orbital distance, that radiation arrives continuously. There is no protective atmosphere known to soften its impact, and there is no planetary magnetic shield that we can confidently say stands between the surface and the incoming particles. For a human body, the numbers become difficult to imagine. A whole body radiation dose of roughly 4 to 5 gray can be fatal without medical intervention, depending on how quickly it is received. Poltergeist exists in an environment where radiation exposure could exceed biological tolerance by enormous margins. The difference is fundamental. On Earth, our atmosphere and magnetic field intercept much of the dangerous radiation arriving from space. Poltergeist has no comparable natural barrier established by observation, leaving its exposed terrain directly connected to the pulsar's energetic output. X-rays can penetrate matter, while gamma radiation carries even greater energy per photon. When these forms of radiation interact with molecules, they can break chemical bonds and alter the structure of complex compounds. Organic chemistry becomes especially vulnerable under sustained exposure. But the radiation field is only part of the environment. A pulsar can also produce a relativistic particle wind, a stream of electrically charged particles accelerated to enormous energies and traveling outward through the surrounding system. These particles interact with planetary atmospheres, transferring energy and gradually removing gas from the upper layers. The process can become self-reinforcing. Radiation heats atmospheric particles, allowing some to escape, while energetic particles strike the atmosphere and physically dislodge additional material. Over geological timescales, these effects can transform a once substantial atmosphere into an extremely thin remnant, or remove it altogether. For Poltergeist, any atmosphere present during formation would therefore face billions of years of exposure. Even a substantial supply of gas could be steadily eroded when the planet remains close to such an energetic source. The surface would inherit the consequences. Rock would remain exposed to high energy radiation, charged particles, and impacts from material arriving through interplanetary space. Without atmospheric protection, even small incoming particles could strike the ground at tremendous speeds. Yet the planet's interior offers a different physical environment. Radiation that reaches the surface cannot penetrate indefinitely through solid rock. Every additional layer of material provides shielding, absorbing and scattering energetic particles before they reach deeper regions. A few miles beneath the surface, conditions could therefore differ dramatically from those above. Internal heat and radioactive decay could maintain chemical gradients, while the surrounding rock blocks much of the external radiation. That does not make Poltergeist habitable. No evidence currently indicates life exists there. It means only that the surface and interior are fundamentally different environments, separated by the planet's own shielding. Above, the pulsar's energy dominates. Below, rock becomes a barrier, and chemistry may persist in places that the radiation never reaches. The pulsar turns with a rhythm that tells us something about its history. At 161 revolutions each second, its rotation is far too rapid for an ordinary neutron star that has simply aged in isolation. Something had to add angular momentum, and that clue points toward a vanished companion. Imagine two stars bound together by gravity, circling a common center. One reaches the end of its stellar life first, leaving behind a neutron star. Its companion continues evolving nearby, and the distance between them can become small enough for gravity to draw stellar material away. That stolen material does not simply fall straight inward. It forms an accretion disk, a rotating stream of gas spiraling toward the neutron star. As the material moves inward, it transfers angular momentum to the compact remnant. The effect is gradual, but immense. Over hundreds of millions of years, perhaps longer, countless particles can deliver their small contributions to the neutron star's rotation. The result is a dramatic transformation. A slowly rotating remnant can become a millisecond pulsar, completing hundreds of rotations each second. We can think of it as stellar recycling. The neutron star remains from an earlier generation, while matter from its companion helps accelerate it into a new phase of life. Yet the process leaves a difficult question behind. What happened to the star that supplied the material? Several possibilities exist. The companion could have lost most of its outer layers, leaving behind a faint stellar remnant. It could have continued evolving until its own structure became unstable. In some binary systems, interactions can remove so much material that the original companion is reduced to a remarkably small remnant. For the pulsar, surrounded by these three planets, the missing companion matters because its disappearance may have changed the entire system. Material left around the neutron star could have settled into a disk after the binary interaction ended. Within that disk, collisions and gravitational attraction could gradually gather fragments into larger bodies. That provides a possible origin for the planets, but it remains a hypothesis rather than a witnessed event. We cannot watch the ancient binary system evolve. Instead, astronomers reconstruct its history from the pulsar's present rotation, the planet's orbits, and the unusual architecture surrounding them. The timing is important. Planet formation around an ordinary young star begins with material inherited from stellar birth. Here, the available ingredients may have arrived much later, after the original star had already died and the neutron star had undergone a long period of interaction. If that interpretation is correct, these worlds belong to an unusual second generation. Their story would begin after stellar death, shaped by matter transferred through a vanished partnership. The pulsar's rapid rotation would then become more than a remarkable measurement. It would be a surviving trace of the relationship that may have supplied the raw material for three worlds. There is another possibility hidden within the system's strange architecture. Some of these worlds may have existed before the star died, carrying their original orbits through the catastrophe that created the pulsar. Survival sounds unlikely, yet the physics leaves a narrow path. A supernova does not distribute its energy evenly in every direction. The expanding debris can form irregular structures, with some regions carrying far greater energy than others. A planet positioned within a weaker section could therefore receive a fraction of the average blast. Distance would matter as well. Even a modest increase in separation reduces the intensity of the incoming radiation and ejecta. An outer planet could absorb less energy than a closer world, especially if the explosion had already been weakened by the star's earlier mass loss. That mass loss may have begun long before the final collapse. Massive stars can shed enormous amounts of material through stellar winds during their later lives, changing the gravitational environment around them. By the time the core finally failed, much of the original envelope could already have been removed. Orbital position adds another layer. A planet traveling along an elongated orbit spends different moments at different distances from its star. If the explosion occurred while that planet was near the farthest point of its path, its exposure would have been reduced during the most dangerous interval. Then comes the neutron star's recoil. An asymmetric explosion can push the newly formed neutron star in one direction, giving it a substantial velocity relative to the surrounding system. The planets would respond to that sudden change in the gravitational center, but their own positions would not instantly disappear. For a planet already moving through space, the outcome depends on timing, direction, orbital speed, and how much mass the star loses. A favorable combination could leave a world gravitationally bound, even after the central star has become something entirely different. This possibility changes how we interpret the three planets. Their present arrangement alone cannot tell us whether they formed afterward or endured the original destruction. The timing measurements reveal their masses and orbits with remarkable precision, but they do not preserve a direct record of each planet's birthplace. Could one world be ancient while another formed later? It is physically conceivable. A surviving planet could provide the gravitational seeds or material that influenced later formation, while newly assembled bodies emerged from debris surrounding the remnant. The distinction matters because each scenario tells a different history. One describes planets that escaped their star's death. The other describes worlds assembled from what remained after it. For now, astronomy leaves both doors open. The system may preserve survivors, second-generation planets, or a mixture of the two, with each world carrying a different chapter of the same stellar catastrophe. For decades, the Arecibo Observatory turned the landscape of Puerto Rico into an instrument for listening across the galaxy. Its enormous radio dish gathered faint signals that ordinary telescopes could never separate from the background, giving astronomers access to changes measured in fractions of a second. The telescope began operating in 1963, built inside a natural limestone depression in the mountains of northern Puerto Rico. Its main reflector stretched 1,000 feet across, creating a collecting surface large enough to detect extraordinarily weak radio signals from distant pulsars. For 53 years, it remained the world's largest single aperture radio telescope until the 500-meter aperture spherical telescope in China surpassed it. When Aleksander Wolszczan examined PSR B1257+12, Arecibo's sensitivity became central to the investigation. The pulsar was more than 2,000 light-years away, yet its repeating signals could be measured with extraordinary precision. Tiny changes in arrival time accumulated across months of observations, revealing gravitational influences that could not be seen directly. We usually imagine a planet being discovered because it blocks starlight or reflects some of it. Here, the telescope detected something far more subtle. It measured the regular radio pulses of a dead star and noticed that their timing shifted in patterns produced by orbiting bodies. Wolszczan returned to Arecibo repeatedly during the early 1990s, refining orbital calculations and testing the emerging planetary system. Each observation added another piece to a problem spread across interstellar distance. The telescope was effectively measuring the motion of a city-sized neutron star by listening to its repeating radio signal. Arecibo had already played another remarkable role in humanity's relationship with the cosmos. In 1974, astronomers used the observatory to transmit the Arecibo message toward the globular cluster, Messier 13. The binary transmission encoded information about humanity, our biology, and our place on Earth, becoming one of the earliest deliberate attempts to send a message toward possible extraterrestrial intelligence. There is something striking about that coincidence. The same instrument that sent a message outward also became the instrument through which we discovered worlds orbiting a stellar remnant unlike our Sunday. Then, in December of 2020, the observatory suffered a catastrophic collapse. The massive instrument platform broke free from its supporting cables and fell into the dish, destroying the telescope that had transformed pulsar astronomy. The structure disappeared, but the observations remained. Data collected at Arecibo continue to preserve measurements of PSR B1257+12, allowing astronomers to revisit the system with new methods and new questions. A telescope can vanish from the mountains, yet the signals it captured remain embedded in scientific history. There is a strange absence in the story of the Nobel Prize. The discovery that first revealed planets around a pulsar never received the distinction that later followed the discovery of a planet around a sun-like star. In 2019, the Nobel Prize in Physics went to James Peebles, Michel Mayor, and Didier Queloz. Mayor and Queloz were recognized specifically for discovering an exoplanet orbiting a solar-type star, a discovery that transformed the search for planets into a central field of modern astronomy. Their planet, found in 1995, arrived 3 years after Aleksander Wolszczan had announced the pulsar planets. That difference in timing is difficult to overlook. Wolszczan's discovery came first, and it revealed something fundamentally unexpected. Planets could exist around the remains of a destroyed star in an environment radically different from the one surrounding our Sunday. Yet the scientific importance of a discovery is not determined by chronology alone. The pulsar planets were difficult to interpret, difficult to verify, and unlike the planetary systems, astronomers already understood. The Nobel Committee's scientific background later described them as possibly connected to the supernova that produced the rapidly rotating neutron star, while noting that such planetary systems appear to be rare. Mayer and Kalos confronted a different kind of surprise. Their discovery showed that a planet could orbit a star resembling our own sun, and its extremely short orbit challenged existing expectations about how giant planets formed. That result helped establish planetary systems around ordinary stars as a widespread astronomical reality. For Wolszczan, the impact was more specialized. His planets expanded the boundaries of where planets could exist, while Mayer and Queloz helped transform the question into a census of worlds surrounding ordinary stars. Both discoveries changed astronomy, but they changed different questions. There is also a practical limit built into the prize itself. A Nobel Prize can be shared by no more than 3 people, and the rules do not permit posthumous awards except in the narrow circumstance where a laureate dies after the announcement. Those rules can force a complicated history of discovery into a very small space. The Nobel Foundation has never publicly stated that Wolszczan was excluded because his discovery involved a pulsar, nor has it offered a formal explanation for why his work was not selected. Any stronger claim would go beyond the evidence. So, the omission remains part of the history. Wolszczan's work stands as the first confirmed discovery of planets beyond our solar system, while the later recognition of Mayer and Kalos helped ignite the enormous search that followed. For you, the distinction may seem strange, but scientific history is rarely a simple race toward one finish line. Sometimes the first discovery opens a door, while another discovery reveals how many worlds lie beyond it. What began with a single pulsar has become a way of listening across the universe. The same principle that exposed planetary companions can now reveal distortions traveling through space-time itself. Pulsar timing arrays bring many rapidly rotating neutron stars into one enormous celestial clock network. Radio observatories on several continents repeatedly measure their pulses, searching for changes as small as millionths of a second across years of observations. Today, the North American Nanohertz Observatory for Gravitational Waves, the European Pulsar Timing Array, and the Parkes Pulsar Timing Array contribute to an international effort involving dozens of millisecond pulsars. Each one provides another reference point, another clock against which the fabric of space can be compared. The target exists at frequencies far below those accessible to ordinary gravitational wave detectors. These waves can take years or even decades to complete a single cycle, stretching and compressing spacetime on enormous scales. Their likely sources are pairs of supermassive black holes. When galaxies merge, their central black holes can become gravitationally bound, circling one another through an immense and gradually shrinking orbit. Each black hole may contain billions of times the mass of our Sunday. The final collision may be dramatic. The long approach is different. For years, decades, or longer, those immense objects can orbit while generating gravitational waves with extraordinarily low frequencies. A terrestrial instrument designed for much faster signals cannot easily sense them. Pulsars offer another possibility. Imagine the distance between Earth and a pulsar changing by a tiny amount as a gravitational wave passes through the region. The pulse still travels at the speed of light, yet its arrival time shifts slightly. One pulsar alone cannot reveal the cause with certainty. A network can. If the same disturbance affects many pulsars in a specific correlated pattern, astronomers can begin separating a gravitational signal from the ordinary variations produced by each individual clock. The pattern itself becomes the evidence. In June of 2023, the North American Nanohertz Observatory for Gravitational Waves announced evidence for a common signal consistent with a gravitational wave background. Other pulsar timing collaborations reported compatible results, strengthening the emerging picture. The signal is often described as a cosmic background, produced by countless massive systems distributed throughout the history of the universe. We are not hearing individual black hole collisions, one by one. We are measuring their combined influence on the timing of distant celestial clocks. That connection reaches back to Aleksander Wolszczan's work at Arecibo. His achievement showed that microscopic timing variations could expose bodies otherwise invisible to our instruments. The technique has since expanded enormously. A single pulsar became a network, a planetary clock became a galactic observatory, and timing measurements became a method for studying spacetime itself. You can trace the lineage directly. A dead star's regular pulses first revealed hidden worlds, and the same precision now helps us measure the universe moving around us. Long before our sun existed, another world was already circling through space. Its name is PSR B1257+12, a planet whose history reaches back almost to the beginning of the universe. This world resides within Messier 4, a dense, globular cluster filled with ancient stars. From Earth, the cluster lies about 12,400 light-years away, placing the planet far beyond the neighborhood of our own galaxy's younger stars. Its architecture is unusual even by pulsar standards. The planet circles a pair of objects, a millisecond pulsar and a white dwarf, locked together in a compact binary system. Farther out, the planet follows its own enormous orbit around both of them. That arrangement has survived for billions of years. Astronomers estimate the planet's age at roughly 12.7 billion years. The universe itself is about 13.8 billion years old, leaving only a little more than a billion years between the birth of everything and the formation of this ancient world. Think about what that means. When this planet formed, the universe was still young. The Milky Way was gathering its structure, and generations of stars had only begun enriching space with heavier elements created inside their cores and during stellar explosions. Earth came much later. Our sun formed roughly 4.5 billion years ago, long after this distant planet had already spent immense ages completing its orbit. Continents had not formed here. Life had not yet appeared on Earth. No human ancestor existed anywhere. Methuselah, as PSR B162026b is sometimes called, was already traveling through its ancient stellar home. The nickname comes from the biblical figure Methuselah, traditionally described as having lived 969 years. The comparison is modest beside a world measured in billions of years. What makes the planet especially valuable is not simply its age. Its existence tells us that planets could form extremely early in cosmic history, when the chemical ingredients available for planetary construction were very different from those surrounding the young Sunday. That does not mean we know exactly what Methuselah is made of. Its great distance and enormous orbital scale make direct study difficult, leaving astronomers to infer its properties from gravity and timing. The pulsar provides the crucial connection. As the planet moves around the stellar pair, its gravity influences the pulsar's motion, producing measurable changes in the arrival times of the pulsar's radio pulses. Once again, an unseen world becomes detectable through the effect it creates. Draugr, Poltergeist, and Phobetor belong to a younger chapter of cosmic history. They are estimated to be several billion years old, yet even these worlds predate Earth. Together, these planets reshape our sense of planetary time. A planet does not need a young star, a calm neighborhood, or anything resembling our solar system to endure across cosmic history. Some worlds began their journeys when the universe was still learning how to build galaxies, and they remain in motion today. A census of pulsar planets begins with an uncomfortable number. Very few are known. Across the Milky Way, astronomers have cataloged thousands of pulsars, yet confirmed planets around them remain exceptionally uncommon. At first glance, that could suggest planetary systems rarely survive around neutron stars. The deeper problem is that our search is heavily incomplete. Finding a pulsar planet requires patience measured in years. Astronomers must record thousands upon thousands of pulses, establish the pulsar's normal timing behavior, and then search for recurring deviations buried within the data. That makes the method demanding. A planet as small as Draugr can reveal itself only through an extraordinarily subtle gravitational influence. Even a large planet may require long observations before its orbital pattern becomes unmistakable. Most pulsars are poor candidates for this kind of work. Young neutron stars often rotate irregularly, with changes in their internal structure, producing timing variations that can overwhelm the signal from an orbiting planet. Millisecond pulsars are different. Their extraordinary rotational stability turns them into natural clocks, making them far better targets for precision timing. Yet, even among the roughly 500 known millisecond pulsars in the Milky Way, only a fraction have received the sustained observations needed for planetary searches. You can see the statistical problem. We are searching a vast population with a remarkably small sample. Thousands of pulsars exist across our galaxy, but only a limited number have been monitored with the sensitivity, cadence, and duration required to uncover planetary companions. Some systems may therefore remain hidden, simply because nobody has watched their clocks long enough. There is another complication. A pulsar can lose its planets, gain new ones, or reshape an existing system through stellar evolution. The planetary architecture we observe today may represent only one surviving stage of a much longer history. Astronomers estimate that the Milky Way contains roughly 100 million neutron stars. These are the compact remnants left behind by massive stars that ended their lives over billions of years. Even a small planetary occurrence rate would change the numbers dramatically. Suppose only 1% of those neutron stars possessed planetary systems. That alone would imply roughly 1 million such systems throughout the galaxy. The calculation is speculative, but it illustrates the scale of what remains unknown. A population that appears almost non-existent in our observations could become enormous once the limitations of detection are considered. There is also a selection effect built into the pulsar method itself. The planets we can detect most easily are those whose gravitational influence produces timing patterns strong enough to survive years of observational scrutiny. Smaller worlds, wider orbits, unfavorable geometries, and systems around less stable pulsars can remain concealed. So, the present census tells us something very specific. It tells us how many pulsar planets we have successfully identified, not how many actually exist. That distinction matters. The galaxy may contain planetary systems around neutron stars that have never announced themselves through a detectable timing signal. Some could be waiting inside archives of old observations, hidden within variations that once looked like noise. Our census is therefore less a final count than a boundary around what we currently know. The rarity of pulsar planets may belong to nature, or it may belong to our instruments. A planet can be measured in numbers, but its name carries another kind of history. For PSR B1257+12, that history was shaped through mythology, language, and a public naming campaign organized by the International Astronomical Union. In 2015, the Name Exo-Worlds campaign invited astronomy organizations and the public to propose names for selected exoplanets and their host stars. The process opened planetary naming to people far beyond professional observatories, creating names that could connect distant discoveries with human traditions. For the three worlds around PSR B1257+12, the chosen names share an unusually consistent theme. Each comes from a tradition concerned with death, spirits, dreams, or disturbances that cross the boundary between the physical and supernatural. Draugr comes from Old Norse tradition. A Draugr is a corporeal undead being, something with physical substance that rises from its burial place. Ancient stories describe these beings as extraordinarily strong and difficult to destroy. That meaning fits the planet's place in the system. Draugr is a world associated with a star that has already passed through catastrophic stellar death, yet the planet remains gravitationally bound to what survived. Poltergeist comes from German. The word describes a troublesome spirit associated with physical disturbances, where objects move or other effects occur without an obvious visible cause. The connection to astronomy is unusually direct. Poltergeist was identified through the gravitational disturbance it produced in the pulsar's timing, revealing its presence through an effect rather than an image. Then there is Phobetor, whose name reaches into ancient Greek mythology. Phobetor belongs to the Waniroi, the spirits associated with dreams, and was traditionally linked with animal forms appearing within them. His role differs from the familiar idea of a nightmare. Phobetor represented the frightening presence within dreams, taking forms that could feel strange, instinctive, and difficult to define. Together, the three names create a pattern that feels almost deliberate in retrospect. One world represents something that survives death, another reveals itself through physical disturbance, and the third belongs to the strange territory of dreams and fear. Yet, there is an important distinction. The International Astronomical Union selected these names through its naming process. The National Aeronautics and Space Administration did not name the planets. That matters because astronomical names are governed through an international system, allowing discoveries to become part of a shared scientific vocabulary rather than belonging to one institution. You can read the three names as a kind of cultural map. They point toward the same boundary that makes this planetary system so unusual, the boundary between what has died and what continues. Draugr, Poltergeist, and Phobetor are therefore more than memorable labels. They preserve the circumstances of a discovery in language, giving three distant worlds names that echo their strange relationship with a dead star. Before January 9th, 1992, planet formations seemed to belong mainly to the beginning of a star's life. Gas clouds collapsed, young stars formed, disks gathered around them, and those disks gradually assembled worlds from their remaining material. That picture was incomplete. The planets around PSR B1257+12 introduced a different possibility. A planetary system could emerge around the remains of a star after that star had already reached the end of its stellar life. This changed the timeline. Planet formation no longer had to happen only during stellar birth. Under certain conditions, material could gather again after a catastrophic stellar transformation, creating worlds from debris left behind by an earlier generation of stars. For astronomers, the implication reached beyond one unusual pulsar. If a rotating disk can gather into planets around a neutron star, then the basic physics of accretion is more adaptable than previously assumed. Accretion is the gradual gathering of matter through gravity. Small particles collide, merge, and become larger bodies, while material with enough angular momentum settles into orbit around a central object. That process had already shaped familiar planetary systems. The discovery showed that similar physics could operate in an environment dominated by a compact stellar remnant, intense radiation, powerful magnetic fields, and extreme gravitational conditions. The distinction between living stars and dead stars had become less useful. A neutron star does not shine like the young sun once did, yet its surrounding environment can still contain enough material, structure, and orbital stability for planets to exist. There was another important shift in observation. Traditional planet searches around sun-like stars often rely on changes in stellar motion or temporary reductions in starlight. Pulsar timing uses something fundamentally different. It measures the arrival times of radio pulses with extraordinary precision, allowing very small gravitational influences to become visible. That method revealed worlds that were difficult to imagine, much less observed directly. Draugr demonstrated that planetary masses could reach remarkably low levels while remaining detectable through timing. Poltergeist and Phobetor showed that multiple worlds could occupy a tightly organized system around a neutron star. The discovery also changed the question astronomers asked about planetary abundance. If worlds can form after stellar death, then surveys of living stars cannot provide the entire census. Some planets may belong to systems whose original stars have vanished, leaving behind only their compact remnants. That possibility expands the planetary population in a profound way. The galaxy may contain worlds created during several distinct chapters of stellar evolution, rather than only during the first stages of star formation. Since 1992, exoplanet discoveries have continued pushing that boundary outward. Astronomers have found worlds orbiting ordinary stars in extraordinary configurations, planets with extreme temperatures, planets smaller than Earth, and systems unlike anything found around our Sunday. Yet the conceptual boundary moved earlier. It moved when 3 planets were found circling a dead star. PSR B1257+12 had no need for a young stellar nursery around it. Its planets demonstrated that planetary architecture could emerge from a later chapter of stellar history after destruction had already reshaped the system. The universe had been building worlds for longer and in more ways than we had imagined. The age of these worlds changes the way we imagine time and space. Long before human history acquired its first written records, Draugr, Poltergeist, and Phobetor were already moving through their ancient orbits. The pulsar system itself is estimated to be between 5 and 6 billion years old, making these planets older than our Sun and older than Earth. When the Sun began forming, these worlds had already existed for an immense span of cosmic history. Earth would eventually become a world of oceans, continents, forests, and civilizations. Here, the passage of time followed another rhythm. Each orbit returned the planets to nearly the same place around their central remnant, while the surrounding galaxy continued changing on scales too vast for any single world to witness directly. Then, in 1990, something remarkable happened. A radio pulse left the system. The signal had begun its journey roughly 2,300 years earlier, around 310 before the Common Era. At that time, Aristotle had been gone for only about 12 years, while the political world shaped by Alexander the Great was breaking apart. No one on Earth was listening for it, yet the pulse continued outward. For more than 2 millennia, the signal crossed interstellar space at the speed of light. During that journey, civilizations appeared and disappeared, languages changed, borders shifted, and generations replaced one another. The radio wave carried no message from an ancient civilization. its information was simpler, embedded in the timing of the pulsar itself. Tiny variations in those arrivals recorded the gravitational influence of worlds orbiting far beyond our reach. Eventually, the signal reached Earth. Aleksander Wolszczan and his colleagues were observing the pulsar with the Arecibo Observatory in Puerto Rico, when those carefully timed arrivals became evidence for planets. A stellar system that had existed for billions of years had finally entered human knowledge. Consider the scale of that coincidence. The planets had no awareness of our species. Their orbits did not change when humans first built cities, crossed oceans, or placed machines beyond Earth. Meanwhile, our entire history unfolded beneath the same distant sky. The Roman Republic rose. The Roman Empire followed. Centuries passed through the medieval period, the Renaissance, and the Industrial Revolution. Humanity eventually reached the moon, while these planets continued following their gravitational paths. Nothing in their environment marked the passing of those human centuries. There were no forests growing, no rivers carving valleys, and no seasonal cycles recording each year. Their history is written differently. A crater may remain exposed for billions of years. A surface feature can preserve an ancient impact long after every human memory has vanished. And the pulses keep arriving. For you, 2,300 years can contain civilizations. For these worlds, it is merely another interval between observations, another stretch of orbital motion beneath the changing galaxy. A clock can keep running long after its maker disappears. PSR B1257+12 is already losing rotational energy, and its gradual slowdown can be measured across astronomical timescales. For us, the change is almost impossible to notice. Across billions of years, however, even a tiny loss of rotational energy becomes significant. A recycled millisecond pulsar, such as this one, may have a characteristic spin-down timescale of roughly 6 billion years, meaning its present rotation belongs to a much longer process of decline. The mechanism is straightforward. Electromagnetic radiation carries energy away from the neutron star, while streams of charged particles continue flowing outward. Each process draws from the pulsar's rotational energy. The faster the star spins, the more power can be available to drive its magnetic activity and radiation. Eventually, the rotation will fall. The pulses will weaken with it. The beam produced by the rotating magnetic field depends upon conditions around the neutron star, and as those conditions change, the pulsar approaches what astronomers call the death line. This is the approximate boundary below which a pulsar can no longer maintain the processes needed to generate its characteristic radio emission. There will be no final explosion. Nothing dramatic needs to happen. The neutron star will remain compressed beneath its own immense gravity, still possessing nearly the same mass it had before, while its rotation continues at a much slower rate. From a distance, it would become increasingly difficult to detect except through the gravitational influence it exerts on anything nearby. For the three planets, the consequences would be strangely simple. Their orbits would continue. Draugr, Poltergeist, and Phobetor do not require the pulsar's radiation to remain gravitationally bound. Their paths are governed primarily by the mass concentrated in the neutron star, and that mass will not suddenly vanish when the pulses fade. The system would therefore enter a different era. Without the pulsar's changing beam dominating the environment, there would be no regular radio signal announcing the star's presence. The worlds would continue circling an object that had become nearly invisible to distant observers. You could imagine the difference as losing a lighthouse while the shoreline remains. The structure still exists, the surrounding geometry remains, but the signal that once revealed it has disappeared. Over immense stretches of time, the planets would keep moving through their established paths. The nearest stars would remain extraordinarily distant, and the thin interstellar medium would provide essentially no drag capable of rapidly altering those orbits. Eventually, even the language of clocks becomes difficult to apply. There would be no civilization nearby to count the years, no seasons to divide them, and no living observer required for the system to continue. Three ancient worlds would remain gravitationally bound to a cooling neutron star, carrying their orbits onward as the galaxy itself changes around them. If we could separate the atoms of these ancient planets, some would carry a history far older than the worlds themselves. Their elements may have passed through stars that lived and died before our sun ever existed. Under the debris disk hypothesis, material from a disrupted stellar system gathered again around the newborn neutron star. Gravity pulled fragments together, allowing heavier elements to become part of new planetary bodies. The worlds would therefore represent recycled stellar matter in one of the most extreme settings known for planet formation. Iron provides one piece of that story. Silicon provides another. Carbon, oxygen, sulfur, and many other elements can trace their origins through generations of stellar evolution, where nuclear reactions transformed lighter atoms into heavier ones. Those atoms eventually escaped their original stars. Some were expelled through stellar winds, others were released during catastrophic stellar explosions. Across immense stretches of time, the material mixed into the interstellar medium, becoming part of the raw substance from which later planetary systems could emerge. Earth belongs to the same broad cosmic process. The iron within our planet, the calcium concentrated in human bones, and the carbon incorporated into living cells all existed before the sun formed. They were manufactured by earlier generations of stars, dispersed through space, and eventually gathered into the disk that surrounded our young star. You are looking at ancient stellar history every time you look at the material around you. The distinction lies in what happened afterward. Earth formed around a comparatively stable star, receiving a long period during which liquid water could persist across its surface. Over billions of years, chemistry gained opportunities to become increasingly complex, eventually producing biology and the environments that support it. The planets around PSR B1257+12 followed another path. Their available environment was shaped by a neutron star, an object left behind after stellar death. The same broad collection of cosmic elements could become part of worlds orbiting in a vastly harsher setting, where intense radiation and powerful magnetic fields dominated the surroundings. That difference matters because planetary formation is not simply a matter of having the right ingredients. The physical environment determines what those ingredients can become. Temperature controls which materials remain solid or gaseous. Gravity determines how matter gathers and how strongly a world can retain its surroundings. Radiation alters chemistry, while time allows some processes to continue long after others have stopped. The atoms themselves carry no memory of where they will eventually end up. An atom of iron does not know whether it will become part of a planetary core, an asteroid, or something within a living organism. Its future depends on the conditions surrounding it and the gravitational architecture that gathers it. So when we compare Earth with these distant worlds, the connection is deeper than appearance. Both may contain matter forged inside ancient stars. Both emerged from material shaped by stellar evolution. Both are products of gravity working across immense spans of time, yet one became a living world. The other became a planet circling a stellar remnant. Same cosmic ingredients, different destination. A planet does not need to resemble Earth to earn its name. Draugr makes that clear with a mass only a small fraction of our own world, occupying a boundary where the distinction between planet and asteroid becomes surprisingly delicate. For centuries, the word planet carried an almost intuitive meaning. We pictured substantial bodies moving around stars, large enough to stand apart from smaller debris. Modern astronomy made that definition more precise, especially after the debate surrounding Pluto and the International Astronomical Union's decision in 2006. Yet the pulsar worlds expose another dimension of the question. Their challenge is environmental. Draugr, with roughly 2/100ths of Earth's mass, is the smallest confirmed exoplanet known. Its existence demonstrates that planetary status does not require enormous size. A body can remain surprisingly small while possessing enough gravity to become rounded by its own mass and maintain a stable orbit within a larger planetary system. The other two worlds occupy a different scale, but they share the same essential distinction. Their surroundings are extraordinarily hostile to known terrestrial life, and their surfaces offer none of the familiar conditions associated with a living planet. Still, astronomy does not classify worlds according to comfort. A planet does not need oceans. It does not require an atmosphere. Nothing in the definition demands forests, weather, or even a living star nearby. The physical criteria concern the body's own gravity, its shape, and the orbit it occupies within its system. That distinction matters. When we look at Earth, habitability can feel inseparable from the meaning of the word world. Our experience gives us oceans, clouds, mountains, seasons, and biology as reference points. But those features describe one particular planetary outcome produced under a particular set of conditions. The pulsar planets widen that picture. Here, planetary bodies can exist around a stellar remnant, far from the familiar architecture of a young solar system. Their existence shows that a world can remain a world after its environment has become almost completely unlike anything humans experience. You could remove the atmosphere, erase the oceans, eliminate every trace of biology, and change the central star into a neutron star. The gravitational identity of the planet would remain. That is where the definition becomes strangely elegant. Planethood belongs to physics rather than hospitality. A planet does not need to support anything. It only needs to exist as a planetary body within the gravitational structure of its system. Draugr, Poltergeist, and Phobetor satisfy that condition from more than 2,000 light-years away. Their surroundings may challenge our assumptions about what a world should be, yet those assumptions are ours alone. The universe has no obligation to make its planets familiar. It only has to make them real. The label dead star becomes misleading the moment we examine what remains. PSR B1257+12 has no nuclear furnace burning at its center, yet its physical presence still reaches across space through gravity, magnetic fields, and radiation. Its original star exhausted the nuclear reactions that once supported it. Hydrogen fusion ended first. Later stages followed, creating heavier elements before the stellar core collapsed under its own gravity. What survived that collapse was an extraordinarily compact remnant, compressed into matter unlike anything found naturally on Earth. The word dead describes the ending of that stellar life cycle. It does not describe the object itself. PSR B1257+12 still rotates hundreds of times each second. Its magnetic field remains immense, anchored within matter crushed to extraordinary density. Charged particles moving through that environment produce beams of radiation that sweep across space as the remnant turns. We can detect those beams from thousands of light years away. That distinction matters because stars are often imagined as engines. While fusion continues, energy generated deep inside the star supports its structure against gravity. Once that source disappears, the star cannot remain in its former state. Its core collapses, and the outer layers can be expelled into space. Afterward, something fundamentally different exists. A neutron star is largely composed of matter packed under pressures beyond ordinary experience. Electrons and protons are forced together, producing neutrons throughout much of the remnant. The result can retain roughly stellar mass within a body only about 15 miles across. Imagine that density without relying on its appearance. Every pound represents an enormous concentration of matter. The transformation also preserves quantities that the original star possessed. Angular momentum survives the collapse, and the shrinking radius makes rotation dramatically faster. Magnetic fields can become enormously stronger as stellar material is compressed. That is why the word dead can conceal more than it explains. A collapsed star has lost the process that once made it shine like an ordinary star. It has not lost gravity. It has not lost rotation. It has not lost its magnetic field. It has not ceased interacting with everything around it. For the planets circling PSR B1257+12, that distinction is fundamental. Their central object does not need to produce sunlight to determine their orbits. Gravity alone is enough to keep shaping their paths through space. And the pulsar's radiation adds another layer of influence. So when we call PSR B1257+12 dead, we are describing a history, not an absence. The star that once existed has ended, but its collapsed remnant continues operating according to some of the most extreme physics in the universe. Death, in this case, marks a transformation. The object remains, the consequences remain, and the three planets remain in orbit around what that transformation left behind. Somewhere in the Milky Way, three worlds may carry the history of another star within them. Draugr, Poltergeist, and Phobetor emerged from material associated with a stellar catastrophe, and their existence gives us a rare glimpse of what can follow a star's destruction. Their formation is thought to involve a disk of material surrounding the collapsed remnant. Debris thrown outward during the stellar explosion could have remained gravitationally bound, eventually settling into orbit around the newborn neutron star. Over time, collisions and accretion would allow that material to gather into larger bodies. Gravity does the patient work. Given enough material and enough time, fragments can become worlds. The process needs no gentle stellar nursery and no newly forming sundae. It can begin with the remains of something that has already ended. That distinction reaches all the way back to Earth. The atoms beneath our feet were assembled long before our planet existed. Iron, nickel, gold, and many other heavy elements were produced through earlier generations of stars and distributed into space when those stars died. Some of that enriched material eventually became part of the cloud that formed our sun and the surrounding planets. We are therefore living inside recycled, stellar history. Our own solar system inherited material from stars that came before it. The pulsar system appears to have done something remarkably similar under conditions that were vastly different. Instead of gathering around a stable young star, material gathered around an extraordinarily compact stellar remnant. the ingredients could still obey the same basic physics. Dust and debris respond to gravity. Collisions redistribute energy. Larger bodies gather more material. Orbital motion shapes the developing system. Given enough time, scattered matter can acquire structure. What changes is the environment. Around our sun, temperatures and radiation allowed chemistry to develop across a wide range of settings. Around PSR B1257+12, the central remnant produced intense radiation while the emerging planets occupied orbits shaped by an entirely different stellar history. You can trace the contrast through their materials. The iron within Earth once belonged to stars that died before the sun existed. The matter forming the pulsar planets also appears to have passed through an earlier stellar life cycle. Both systems, therefore, contain physical records of cosmic generations that came before them. Yet one environment eventually produced oceans, atmospheres, biology, and observers capable of looking backward into that history. The other produced worlds around a neutron star. That difference reveals something important about planetary formation. Building a planet may be easier than building the conditions that transform a planet into something chemically complex. Gravity can gather matter. Time can reshape it. But the environment surrounding that matter determines which possibilities remain available. For billions of years, these worlds have followed their paths around a remnant star. Their existence tells us that planetary systems can survive beyond the ordinary boundaries of stellar life, and perhaps even emerge from its aftermath. A star can end without taking every orbit with it. Its material can continue, its gravity can remain, and from the remains of one generation, another generation of worlds can take shape. 3 planets can remain completely indifferent to whether anyone ever finds them. Their orbits continue through the same gravitational laws that shape them, carrying them around PSR B1257+12 across spans of time almost impossible to place inside a human lifetime. Draugr, Poltergeist, and Phobetor have no need for witnesses. Their existence does not depend on recognition, names, or photographs. They remain worlds because matter, gravity, and orbital motion continue to define them. That changes something on our side of the universe. Before their discovery, every confirmed planet belonged to a planetary system we could imagine in familiar terms. The search for other worlds was already underway, but the basic picture remained centered on stars resembling our sun and systems born around them. Then a pulsar introduced a different possibility. Aleksander Wolszczan was examining the timing of radio pulses when tiny irregularities appeared in the arrival pattern. The deviations were measured in millionths of a second. Their source was gravitational. 3 planets were moving around the pulsar. For the first time, we had evidence that planetary systems could exist around the remains of a star. The discovery did more than add 3 objects to a growing catalog. It expanded the range of environments in which planets could exist. That expansion has continued ever since. Astronomers have since found worlds orbiting red dwarfs, giant stars, white dwarfs, and other unusual stellar environments. Some are scorched by intense radiation. Others may be covered by global oceans, locked into strange orbital resonances, or wandering through space without any parent star at all. The universe keeps offering variations. Yet the pulsar planets remain unusual because their existence was revealed through timing rather than direct light. We cannot simply point a telescope toward them and watch their surfaces. Their presence emerges from the precise rhythm of their parent pulsar. That rhythm became our evidence. Think about what that means. The planets were never trying to announce themselves. Their gravity merely altered the motion of their central object by an amount small enough to hide inside the measurement, yet large enough for careful observation to uncover. You and I only became aware of them because someone noticed the pattern. The discovery, therefore, carries a deeper lesson about exploration. What we find depends partly on where we look, but also on what signals we have learned to recognize. A world can reveal itself through reflected light. Another can betray its presence by dimming its star. These three announce themselves through the movement of a cosmic clock. And that leaves us with a broader view of planetary diversity. A planet does not need to resemble Earth to qualify as a world. It does not need oceans, clouds, seasons, forests, or a welcoming atmosphere. It only needs the physical conditions that allow matter to gather, remain bound, and persist as an organized body. Draugr, Poltergeist, and Phobetor occupy that definition from an extraordinary distance. Their discovery reminds us that the universe was never obligated to match the limits of our imagination. We simply had to become precise enough to notice where those limits ended. The surface of a pulsar planet may be a poor place to search for life, yet a planet is more than the few miles of rock we can imagine from above. Beneath that exterior, pressure, chemistry, and stored energy create environments that are almost impossible to observe directly. Poltergeist and Phobetor receive intense radiation from their central neutron star. Any exposed atmosphere would face severe irradiation, while their surfaces would lack the stable conditions associated with life on Earth. But radiation becomes less important as rock accumulates overhead. Depth changes the equation. On Earth, some of the most persistent ecosystems exist far beneath the surface. Microorganisms called chemolithotrophs obtain energy from chemical reactions involving minerals and dissolved compounds rather than sunlight. Some occupy fractures deep within Earth's crust where surface conditions barely influence their existence. That does not make the pulsar planets habitable. It gives us another boundary to consider. If these worlds contain substantial rocky interiors, their deeper layers could be shielded from external radiation by enormous amounts of material. Residual heat from their formation, together with radioactive elements inside the rock, could maintain temperature differences and chemical gradients for long periods. A chemical gradient is simply a difference in concentration or energy between neighboring regions. Such differences can provide usable energy when matter moves toward a more stable state. We know this principle from Earth. Hydrothermal systems, mineral reactions, and deep geological environments can sustain chemistry without sunlight. Some theories for the origin of life itself involve environments where minerals, heat, and chemical gradients interacted over immense stretches of time. The pulsar planets offer no evidence that such processes produced biology there. We have detected no organisms, no atmosphere associated with life, and no chemical signature that could establish biological activity. That distinction matters. Astrobiology begins with evidence, but it also studies the conditions that make evidence possible. A world can be inhospitable at its surface while retaining regions where chemistry behaves differently. For us, the deeper question concerns energy. Life requires organized chemical processes that can remain out of equilibrium. If a planet possesses internal heat, reactive minerals, and pathways for matter to circulate, some forms of chemistry could remain active even without starlight. Whether those ingredients exist inside Draugr, Poltergeist, or Phobetor is unknown. Their masses and compositions cannot currently be mapped with enough detail to reconstruct their interiors. Still, their existence changes how broadly we should define a planetary environment. A world does not have to resemble Earth from orbit to contain complex chemistry beneath its exterior. The universe can hide its most interesting conditions below surfaces we cannot see. And that leaves life with a larger possible laboratory, extending beneath worlds where sunlight never reaches. The modern catalog of exoplanets began with an unexpected entry: 3 worlds circling a stellar remnant. Before astronomers could count thousands of distant planets, they first had to establish that planets beyond our solar system could be detected at all. That proof arrived through timing. When Aleksander Wolszczan and Dale Frail announced the planetary system around PSR B1257+12 in 1992, they established something fundamental. A planet did not have to reveal itself by crossing the face of its star. Its gravitational influence could be measured through changes in the rhythm of a pulsar. That principle opened a new observational path. 3 decades later, thousands of confirmed exoplanets occupy the astronomical catalog. They range from enormous gas giants to worlds smaller than Earth, orbiting stars that differ in temperature, age, mass, and behavior. We now recognize planetary systems as remarkably diverse. The techniques have multiplied as well. Transit observations reveal planets when they periodically block a fraction of their star's light. Radial velocity measurements detect the motion a planet induces in its star. Direct imaging can separate certain young, massive planets from the glare of their parent stars. Each method reveals a different part of the planetary population. The Kepler Space Telescope transformed the census by monitoring hundreds of thousands of stars for repeated changes in brightness. Its observations showed that planets are common throughout the galaxy, including small worlds that would have been extraordinarily difficult to find through earlier techniques. Then came the Transiting Exoplanet Survey satellite, extending that search across much of the nearby sky. Its targets include bright stars whose planets can be studied in greater detail with other observatories. The James Webb Space Telescope has taken that process further. When a planet passes in front of its star, some starlight travels through the planet's atmosphere. Molecules absorb particular wavelengths, leaving patterns that astronomers can analyze. We can now study distant atmospheres without ever visiting those worlds. That capability rests on a foundation established decades earlier. The first pulsar planets demonstrated that planetary signals could be extracted from extraordinarily precise astronomical measurements, even when the planets themselves remained invisible. Nothing about that first system resembled the planetary systems later discovered around ordinary stars. That difference made the discovery especially important. The first confirmed worlds beyond our solar system were not familiar Earths waiting beneath another sun. They were Draugr, Poltergeist, and Phobetor, orbiting a neutron star under conditions far removed from those surrounding Earth. Their strange beginning became part of a much larger scientific history. Today, when astronomers measure atmospheric chemistry, estimate planetary populations, or search distant worlds for possible signs of life, they work within a field that did not yet have its first confirmed entries before 1992. The catalog now stretches across thousands of worlds. Its first pages were written by 3 planets no one expected to find. Across the constellation Virgo, a stellar remnant continues its ancient rotation, carrying 3 planets through space with it. PSR B1257+12 spins 161 times each second, repeating a rhythm that began billions of years ago. The system is roughly 5 to 6 billion years old. Long before human beings measured time with clocks, these worlds were already circling their central remnant. Their orbits have persisted through ages of cosmic change, while the star itself has gradually surrendered the energy that once powered its pulses. Three planets remain. Draugr, Poltergeist, and Phobetor occupy a compact system unlike the familiar architecture of our solar system. Their names come from legends of revenants, spirits, and dream beings, yet their motions require no mythology. Gravity keeps each world on its path, governed by the same physical laws that shape planetary systems across the galaxy. No observer needs to be present for those laws to operate. That may be the most striking feature of this distant arrangement. Its planets do not orbit for an audience. Their surfaces do not record human history, and their existence does not depend upon being discovered. For billions of years, they continued their cycles without anyone on Earth knowing they were there. Then, in 1990, Aleksander Wolszczan began examining the timing of the pulsar's radio pulses at the Arecibo Observatory. Tiny departures from the expected rhythm revealed that the pulsar was being gravitationally tugged by unseen companions. We eventually learned what those variations meant. The discovery changed our map of planetary possibility. Before it, our only confirmed planetary system was our own, leaving astronomers with a single example from which to imagine how worlds might form. Afterward, the galaxy became a much larger laboratory, containing planets around stars unlike the Sun, and systems arranged in ways our earlier expectations had never required. Today, thousands of confirmed exoplanets have expanded that picture. Some circle ordinary stars. Others occupy extreme environments, follow unusual orbits, or possess properties that would have seemed improbable before the first pulsar planets were known. Yet those first three still occupy a special place. They remind us that discovery does not always begin with seeing a world directly. Sometimes you find it by noticing that something else keeps time imperfectly. A distant pulse arrives a fraction early, then late, then early again, tracing the gravitational signature of an unseen companion. From those minute variations came a new category of worlds. PSR B1257+12 remains far beyond any journey we could make, carrying its three planets through the galaxy. We can only receive their signals, measure their motions, and reconstruct their existence from patterns written into radio waves. The star has changed. Humanity has changed. The planets continue their orbits. And somewhere beyond our reach, the first confirmed worlds beyond the Sun remain exactly where gravity placed them, circling a stellar remnant that never needed us to be there.